So, um, I just want to I want to kick today off by starting to talk a little bit about integration. We mentioned integration really briefly at the beginning of the semester, at the very beginning. I mentioned that there's two major problems in calculus. There's the problem of differentiation, which up until like today, we've been studying exclusively. Differentiation is the problem of finding the instantaneous rate of change of a function or the slope of a function at a given point, the slope of the tangent line, right? And integration is the problem of finding the area beneath a curve, right? So let's, okay, well, let f of x equal x squared plus 1 and consider the area enclosed by f of x, the x-axis, the y-axis, and the vertical line x equals 2. So maybe we have our axes here, right? Maybe we'll have 1, 2. Whoops, that's too low. So we get the graph of the parabola shifted up by 1. Um, Looks something like this. So what we're trying to do is we're trying to find the area of this region in here. So any ideas on how we can do that? If I just told you, hey, let's estimate this area, what would you do?
Numerical integration. Say we could split it into chunks and then solve for
Yeah,
the area of each
that
one of
sounds
them.
suspiciously like someone who's seen this before. But
Okay.
so the thing I always did when before I knew anything about calculus was I was always taught as a kid that like okay, well we're gonna take all the squares, right, and we're gonna count the number of squares, like the number of full squares that I can find, right? That's a full square. That's a full square. Maybe that's almost a full square, right? And then we can like estimate these by saying, all right, well, this one and this one makes a full square, or sorry, this one here and this one here approximately makes a full square. Maybe this one here and this one here makes a full square, etc. And we could just add stuff up like that. And that's a perfectly reasonable method if you're just trying to estimate one thing. But unfortunately, it's not a method that allows you to enhance it in any real way to make it more accurate. We could make all of those squares smaller, but it's a little bit overkill to divide it into that many squares. Instead, um, one of the really useful things that you can do here is maybe we can break it up into um, a couple of different regions. All right. Maybe we can say, all right, I'm basically just going to take this rectangle here. And I'm just going to use rectangles for this. Maybe this rectangle here, maybe this rectangle here, and maybe this rectangle here. In other words, we're just using basic geometric objects that we can easily find the area of, right? So this first rectangle here has a height of 1 and a base of 1/2. The second rectangle here has a height of 1.25 and a base of 1/2. This third rectangle here has a height of 2 and a base of 1/2. And the fourth rectangle here has a height of 3.25 and a base of 1/2. Okay. So by doing this, by taking our rectangles here and adding them all up, we can come up with an estimate. And our estimate for this area ends up being 3.75. There's also the option to so what I did is I chose some rectangles where the left-hand side of the rectangle always met up with the curve, right? We could also take the right-hand side of the rectangle instead and have that meet up with the curve. And that would give us a different estimate, right? One that's, instead of the blue estimate here is a little smaller than our curve, our green estimate is going to be a little bit bigger than the curve. The green estimate has, the first one has a height of 1.25. The second one has a height of 2. The third one has a height of 3.25. And the last one has a height of 5. When we add all of those up, the area of our green rectangles ends up being about 5.25. So our true value should lie somewhere between these two numbers, somewhere between 3.75 and 5.25. Does everyone agree with that? How can we make this version of the estimate better? What's one thing we can do to try and get a better approximation? Because both of these are pretty far off, right? The green approximation adds all of this extra area here, right? And the blue approximation misses all of this area here.
We could make the step function 2 as where it's infinitely approaching the function.
It's like you guys have seen this before.
It's so weird, right?
Yeah. So there's actually really, I see two really obvious options here. The first one is to do both of them and then take the average. Mathematically, that's actually a little bit more akin to, instead of using triangles, or instead of using rectangles, to use trapezoids with these straight lines here. So essentially, we're sort of de-resing the curve. Instead of having a really nice smooth curve, we're taking these nice straight geometric edges, right? And we're finding the volume of the trapezoids that we find this way. This mathematically ends up being the exact same thing as taking the average of the two, and that gives us a estimate of about 4.75. That's not right. 4.5. The other option, so the problem with this is that there's not a really obvious way to make this even better, right? Once we've done that, how do we get even closer to reality. Well, that's tough. I think the thing we actually need to do is to make more rectangles. So we could take this same curve oops, that should be there, 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 there. Something like that. And then instead of doing 4 rectangles, we could do 8 rectangles. And yeah, if we wanted to brute force something like this, it would definitely be better to make a computer do this. This seems like something a computer would be really good at and something that humans are not very good at, right? Anything that requires a ton of really minor rote calculations is definitely a computer ballgame. So now we have 8 rectangles instead of 4 rectangles. And I think our estimates are definitely a little bit better. Now we have less extra area, right? We've gotten rid of this chunk here in the green area, right? That's now this rectangle up here that was in our previous one is now gone, right? Now that's not where we've gotten rid of a bunch of our overestimate, etc. Right? So making more rectangles is better. In fact, when we use 8 rectangles, we get the green estimate is going to be, so the green estimate, the higher estimate will be about 5.187. And the blue estimate, our lower estimate, will be about 4.1875. And then the theory here that's going to link this idea of the area beneath the curve problem to the theory behind derivatives is what Nick just alluded to. It's that what if we could have infinity rectangles? Well, we can't actually have infinity rectangles because if we had infinitely many rectangles, then all of the rectangles would have to have 0 width, right? And then we end up in a weird situation with infinity times 0, and infinity is not a number anyway, so like, how the heck do we deal with that? And the answer is limits. So the thing we need to do in order to make this idea of rectangles work and give us a really, really great solution for what the area beneath a curve is to actually be really careful in how we pick our rectangles so that we can then have a really nice way of making of applying a limit and making infinitely many, infinitely thin rectangles, right? And what you can sort of think of, the way I sort of think of this is that as we get more and more rectangles, it's like our image becomes higher and higher resolution. Sort of the pixels that make up the interpolation between the line get smaller and smaller and smaller until it looks more and more and more like a straight line, or like the actual curve, right? So the more rectangles that we use, the closer to reality we're at. So it turns out that the nicest way to parameterize these rectangles is actually we're going to need to use some notation first off. We're going to need to do sigma notation. We need to do sigma notation because we're going to be talking about adding up a giant load of numbers all together, and they're all going to be very similar numbers. So we need some compact way of writing this. I don't want to write a plus b plus c plus d plus e dot 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 all over and over and over again. I want a nice compact way to write a sum. Okay, so a definition. If a sub n is a sequence and j and k are both integers greater than or equal to 0, then we define the series n equals j to k of a sub n to be a sub j plus a sub k, or rather a sub j plus 1 plus dot 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 up to a sub k minus 1 plus a sub k. So quickly, just to note, there is a term inside a term here in sequence. A sequence is just a list of numbers. They don't necessarily have to be integers. They can be any numbers. For us, our sequences will always be of real numbers. And for us, our sequences will be defined pretty explicitly. Okay, so we're not going to mess around too much with sequences. But basically what this is saying is that this notation here with the sum means that we're going to add up all of the terms of a sequence, all of the numbers that live in that list of numbers, and then we're going to add up all of the terms between whatever j is and whatever k is, right? So, for example, the sum of from n equals 3 to 7 of 2n is going to be 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6 plus 2 times 7, which ends up being 60. So when we're talking about this sigma notation, we call it sigma notation because this letter here, this big weird E thing, this is the Greek letter capital sigma. Okay. Sometimes it's called the summand, S-U-M-M-A-N-D. And then on this capital sigma, we have bounds. We have a lower bound and an upper bound. And then we have the things we're actually adding up. So this notation is going to be really nice for this because if I can give if we can give a generalized description of the type of objects we're adding up in a nice mathematical way, then we can put it into this nice sum notation. and hopefully they're indexed in such a way that it makes sense for us to take a limit of that whole thing. Does anybody have any questions about sum notation here, sigma notation?
If you've ever done any
go ahead.
programming, it helps to think of it as a for loop.
Yeah, it basically is a for loop, right? It's is it a for loop or is it more like an iterating if loop? I think it is a for loop. Yeah. So basically, you're taking for the numbers between 3 and 7, right, inclusive, multiply it by 2, and then add all of those sums together.
Will we always be given the upper and lower bounds?
Well, not kind of, yeah. The upper and lower bounds are not always going to be a number, unfortunately. The lower bound will almost always be a number. For us in this class, the lower bound is always just going to pretty much always just going to be 1. The upper bound is a little trickier. We'll see in just a second that the upper bound is going to be something that is going to change.
Is there a way to specify if n can increment by a number other than 1?
No. For some notations, because we're explicitly using sequences, sequences are indexed by natural numbers, so they always increase by 1, right? If I wanted something to increase, like if I wanted to take every other term of a sequence, then I would have to define a new sequence that gave me every other term of that sequence. Does that make sense?
Yeah, I get it.
Okay. So it's not quite as versatile as a for loop.
Yeah.
There is there's also something called product notation that uses the exact same format, but instead of a sigma, it has a big pi. That again has a lower bound and an upper bound of some sequence, and that is a sub j times a sub j plus 1 times times a sub k minus 1 times a sub k. This is totally irrelevant to our class. We're never going to touch it, but it is nice in case you ever do run into it. It is a nice thing to know about. So these sums, we're going to use them very briefly to define what we're going to be doing with these rectangles, and then we're not going to do a whole ton with them. You'll do a couple of exercises with them, and you'll need to be able to evaluate them with the limits and stuff. But these will come back in a really big way in Calc 2. So. Also, a quick note. The sum from n equals 0 to 0 of a sub n is equal to 0. Or rather, I should say even more explicitly, the sum from n equals I to I of a sub n is equal to 0. If you're ever adding up all the terms, sorry, no, from I to I minus 1, I should say. If ever the ending term, the upper bound, is smaller than the beginning bound, the lower bound, then this is called the empty sum, and it's defined to just be 0. You're adding up 0 terms, so your answer should end up just being 0. So there are some really nice properties of sums that you see. A lot of them are going to hopefully remind you of hold on. Yeah, Okay. Some of them should remind you of properties of derivatives. For instance, if we have the sum from n equals j to k of c times a sub n, that's going to be c times the sum from n equals j to k of a sub n. Similarly, if we have the sum of two different sequences, a sub n plus or minus b sub n, then we can split those up. That'll be the sum from n equals j to k of a sub n plus or minus the sum from n equals j to k of b sub n. Okay. Note that if you multiply, if you have the multiple or the product of two sequences, then you can't break it up across products. This only works across addition and constant multiples, because those are things that we could factor out of every single term, right? And you're not able to reorder around multiplication. So let's go back to this idea of using these rectangles to find this area, right? 1 second, let me find the definition I was looking for. There we go. So let's head back to finding areas by limits of sums of rectangles. We probably need a better name for that, and there is a better name for this idea. It's called quote unquote, not quote unquote, it's called Riemann integration, or sometimes a Riemann sum, or Riemann rectangles, or Riemann sum. So Riemann is one of the guys that so Newton and Leibniz sort of came up with calculus, and they sort of invented the things that hold calculus together in the 17th century, something around there. And they did a bunch of really amazing work, and they didn't prove anything, man. Like, they just found a bunch of stuff that worked and said, hey, this all works, cool, we're going to use it to do some physics, which is, you know, nice. They found stuff that worked, and it turns out that they were both totally right all along, but they never did any sort of they never formalized it in a really meaningful way that was really self-evident, right? That they never sat down and actually went for basic principles and showed that all this stuff worked. In the 1800s, there was a big wave of mathematicians who basically went back and formalized calculus into a field called analysis, and went through and proved all of these ideas that they came up with. And Riemann was one of the most influential of those. That's why his name is on this idea. This was how this was the way that he chose to parameterize integration. Okay. And Riemann integration is essentially this idea that we're taking rectangles, and there's a lot of different ways to parameterize the rectangles. So for us, from this point forward, all of our rectangles will be right-hand rectangles. This means that the rectangles will touch the curve in their right hand corner. So one side of the rectangle will lie along the x-axis, and then the other side of the rectangle, the right hand corner of the other side of the rectangle will lie along the curve, right? So if we go back up at our examples earlier on, those are those green rectangles, okay? The green rectangles are right hand rectangles, the blue rectangles are left hand rectangles. So we're just going to use right-hand rectangles. We technically, the morally correct thing to do is actually to use upper rectangles and lower rectangles. And the only thing you really actually have to do is to use any point. The rectangle just has to touch the curve somewhere. But it's going to make our definition a lot cleaner if we just use right-hand rectangles, because we don't have to mess with a bunch of stuff. You may see other sources using some weird notation for this exact thing we're about to show. Particularly Paul's Online Math Notes uses the sort of weirder notation. We don't need to actually do that in order to be formally correct about what a Riemann sum is. It turns out that no matter where the rectangles touch the curve, the result of us, as we shrink the size of those rectangles and add more and more rectangles, we're still going to approach the correct area. It doesn't matter where they actually touch. So each if we have n rectangles, over the interval a to b, then each rectangle will have width equal to b minus a divided by big N. So in our earlier example there, A was 0, B was 2. So the width of each of these rectangles, we had 4 rectangles, would be 2 minus 0, which is 2 divided by 4, which is 1/2. So that's our 1/2, right? So we want to define a sequence we're going to call it x sub n, right? And x sub n is going to be let's call this with delta x. B minus a over n. The width of each rectangle is delta x. It's the change in x from one side of the rectangle to the next side of the rectangle, right? So this x sub n is going to be a plus n times delta x. In other words, x sub 1 is going to be a plus delta x. x2 is going to be a plus 2 delta x, right? In other words, the first term of our series, or of our sequence here, is going to be the starting x coordinate. And then we're going to add 1 width of our rectangle. Our second term in the sequence will be our starting x coordinate plus 2 widths of rectangles. In other words, if we go back to our case here, our starting coordinate was 0, And then if we take the first term of our series, x sub n, a plus x sub n, we're going to get, or a plus delta x, we're going to get from 0 to 1/2. So the first term of our sequence will give us 1/2. And then the second term will give us 0 plus 2/2. So we'll get here on our second term, our third term, and our fourth term. Etc., 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 for however many rectangles we have. So the reason why we're defining this in sort of a weird way is because now we actually have a really, really nice equation for the area of each one of these rectangles, right? So the area of each one of these rectangles, we know the right-hand side of the rectangle is going to hit the curve, right? So the height of the rectangle is just going to be the value of the function at that point. So the height of each rectangle is the value of f of x at x equals x sub n, right? We decided that those are the x coordinates that we're going to be using to plug in, right? So the height is just going to be the associated y coordinate. And the width of each rectangle is delta x, right? That was how we defined delta x in the first place, right? So that means that the area of each rectangle is f of x sub n times delta x. So if we want to add up all big N of these rectangles, we can write our sum notation. The sum from n equals 1 to big N of f of x sub n times delta x. And that is actually, for all intents and purposes, this is the definition of the integral. Okay, so let's write that down formally. Definition. So we're going to let f of x be continuous on a to b. Then the Riemann integral of f of x on a to b written the integral from a to b of f of x dx is the integral from a to b of f of x dx is equal to the sum from n equals 1 to big N. Sorry, I should say that it's equal to the limit as big N goes to infinity of the sum from n equals 1 to big N of f of x sub n delta x, where delta x equals b minus a over big N, and x sub n equals a plus n delta x. So this is a big important definition, okay? This is how we are going to define and evaluate integrals for at least today. Does anybody have any questions with where we're at right now? Is my stream having troubles for anybody else?
It's working
Yeah,
fine
I
for
was
me.
breaking up.
Okay. I only hear mild complaints, so I'm gonna keep on trucking. So let's look at let's go ahead and try to evaluate an integral. Oh, I suppose I should have actually I did this a little bit out of order. While I defined the Riemann integral this way, the primary definition of integral that we should be using the integral of f of x on a to b is written integral from a to b of f of x dx, and is defined as the integral from a to b of f of x dx is the signed area between f of x and the x-axis. We often sort of casually refer to the integral as the area beneath the curve, but that's actually a little bit misleading. The integral is not actually the area beneath a curve. It's the area between the curve and the x-axis. If the curve is above the x-axis, that's the same thing. If the curve is below the x-axis, then we get something weird that happens, okay? So note, if f of x is less than 0 on AB, then the integral from a to b of f of x dx is also going to be negative, right? So I probably made a flippant joke at some point during optimization and said, oh, well, area can never be a negative quantity. Area can't be a negative quantity. This is why we're not actually talking about area. We're talking about this signed area, okay? It's more akin to like displacement versus distance, right? So we're measuring an amount of displacement rather than an amount of distance. There is such a thing as, like, if you have a velocity function, you have a direction on it. It has a forwards motion and a backwards motion, right? So integrals have the same idea. Negative or positive values of the integral will give you positive areas. Negative values of the function will give you negative areas. Okay. It still does measure that geometric area. It's just that anything below the curve will be subtracted from the total instead of added to it. Or anything below the x-axis will be subtracted from the total instead of added to it. So let's go back to f of x equals x squared plus 1. So we want to evaluate the integral from 0 to 2 of x squared plus 1 dx. That's basically the very first question that we asked today. That's basically what we asked, okay? What is the area between this curve and the x-axis from 0 to 2? And in order to evaluate this using the Riemann sum, we should set it up appropriately, right? So we need to identify what x sub n is, or rather we need to identify what delta x is. And we need to identify what x sub n is. So our delta x is b minus a divided by big N. So that's actually going to be b minus a is 2 minus 0 over big N, which is 2 over n. And x sub n is going to be a plus little n times delta x. In other words, that's going to be 0 plus n times 2 over big N. So x sub n is 2 little n over big N. So our integral from 0 to 2 of x squared plus 1 dx is actually equal to the sum from n equals 1, or sorry, the limit from n to, as big N goes to infinity, of the sum from n equals 1 to big N of, we have 2n over big N quantity squared plus 1. This is f of x sub n. And then we're going to multiply that by 2 over big N. Let's expand some stuff here. We get the limit as big N goes to infinity still of the sum from n equals 1 to big N of on the, so when we expand this square, we get 4n squared over big N squared plus 2 or plus 1 still times 2 over big N. And then we can distribute our 2 over n. So that's the limit from n as big N goes to infinity of the sum from n equals 1 to big N of 8n squared over big N cubed plus 2 over n. And right now, this still seems like a really hard problem. It still seems like I'm asking us, or that we're being asked to add up an infinite amount of things. And that's true right now. Things are sort of a mess, right? So let's go ahead and see if we can pull anything out of our sums or expand these sums in any real way. One thing to notice here is that we have the sum overall of the sum of two different sequences here, right? We have this sequence over here that's 8n squared over n cubed plus 2 over big N, right? So we can actually split this up into two different sums. We can split this up. The limit is still going to be all the way on the outside here. We're going to evaluate that at the end. But we have now the sum from n equals 1 to big N of 8n squared over n cubed plus the sum from n equals 1 to big N of 2 over big N. This guy over here on the right, we're just adding 2 over n to itself n times, right? If big N was 8, this would be 2 over 8, and then we would add it to itself 8 times. That's just 8 times 2 over n. Okay, or that's just 8 times 2 over 8, which is just 2, right? So this guy over here is going to just evaluate to 2. in just a second, we're going to talk about a little bit more details, on a little bit more versatile way to note that this is 2. Okay. We still have our limit as big N goes to infinity. For this one over here, this big N cubed, it's actually constant with regards to whatever this big N is. Or with regards to the index of this sum. The index of the sum is little n. Big N is only going to change when we actually apply our limit at the end. So we can actually pull our big N cubed and our 8 out of this sum. So we get 8 over big N cubed times the sum from n equals 1 to big N of n squared. So that was a little bit hand wavy, and we'll talk a little bit more. We can definitely talk more about why I did what I just did there. Does anybody have any questions about that, or does it seem clear right now?
So I guess, could you explain again why we could pull out 8 over big N cubed?
Are you okay with why we can pull out the 8?
Yes.
Okay, because the 8 is just multiplying every single term, so we're sort of just factoring it out, right? And the n cubed we're actually factoring out as well. If we knew n was like 4 or something, right, then this would just be 4 cubed. And it wouldn't, this value of big N here doesn't depend at all what the sum is. Every single time we add something up in this sum, this big N value is the same thing, right? So according to the index of the sum, big N is constant. We can't pull it out of the limit because it's definitely not constant according to the limit, right? Like the limit is changing what big N is. But this sum here from little n equals 1 to big N doesn't change the value of big N at any point. So big N is constant while we're evaluating that sum. In other words, if I was to evaluate this thing, right, as doing a limit, we might pick some value for n, like n equals 5,000 or something, right? And then we could evaluate that at 5,000. But once we've picked that value of n according to what our limit says it is, it doesn't change. It's constant from that point forward. Does that help?
It does. Thank you. That
okay.
It's clicking.
Okay. We'll keep practicing with these. So the last tricky thing we need to do is we need to know what the heck this is. The sum from n equals 1 to big N of n squared is. And it turns out that if you are adding up the sum from n equals 1 to some other number of n squared, that ends up being exactly so the sum from n equals 1 to big N of little n squared is exactly big N times n plus 1 times 2n plus 1 over 6. I will give you, in just a second here, I'll give you a handful of these formulas to know. We are not by any means going to be able to evaluate many integrals, Riemann integrals by hand using this limit definition. There's going to be a very select few that we can do. This happens to be one of them, and it's because of this known formula. So this then becomes the limit as big N goes to infinity of 8 over big N cubed times big N times big N plus 1 times 2 times big N plus 1 over 6 plus 2.
So I've been wondering this whole time, why is little n equal to 1? Shouldn't it be the beginning of the interval?
Yeah, it is. But how many? So we wanted to start at 1 because we're taking our right hand rectangles, right? And the very first rectangle has a height not at the very beginning of the interval, but at one step into the interval. Right?
Okay, that makes sense.
Yeah, so we don't want to index at 0, we want to index at 1. We're going to index from 1 to big N. If we were doing left-hand rectangles instead, our definitions would be exactly the same. Our index would just go from 0 to big N minus 1, and then we'd have to shift by 1 to make all the math work. It's just cleaner to use the right-hand rectangles than the left-hand ones. And that means that we don't actually start at the beginning of the interval, we start one step over from the beginning.
Okay.
So out here, I want to FOIL out this numerator. We're going to end up with the limit as big N goes to infinity of 8 over n cubed times, it's going to be 2n cubed plus 3n squared plus n divided by 6, still plus 2. And then we can distribute here and we get the limit as big N goes to infinity of 16 n cubed plus 3n plus 24 n squared plus 8n over 6n cubed plus 2. We can simplify this somewhat before we even think about the limit. An n cancels out of every term. And I think a 2 cancels out of every term. So we have the limit from as n goes to infinity of 8n big N squared plus 12 big N plus 4 divided by 3 big N squared plus 2. And now we can actually just apply this limit, right? We know how to do that. We've been dealing with that all semester long. We can apply this limit, and what's going to happen is that this is a rational function of n, where the degree of the top and the degree of the bottom is the same. So the limit as n goes to infinity is just going to be the ratio of the leading coefficients. So this is just 8 over 3 plus 2, or 4.33 repeating, which is in fact the exact value of our integral. And that is that does sit nicely between our two integrals, or our two estimates, right? With our 4 rectangles, we had 5.25 and 3.75. And that 4.5 was close, but it wasn't quite right. It was a little bit too big. And for the 8 rectangles, 5.1875 and 4.1875. So, yeah. And that's Riemann integration, basically. This is sort of like the definition of the derivative, in that this is a really, really, really absurd way to do integrals. Unlike the definition of the derivative, though, sometimes you do integrals this way. Okay? For the definition of the derivative, nobody ever does derivatives using the definition of the derivative. It's kind of an insane way of doing it. The definition of the derivative is important to understand some subtleties about the theory behind derivatives, but you're never actually going to use it to take a derivative. Integration is a harder problem in general, okay? Differentiation is nice. The tools I've given you so far basically enable you to differentiate any function that you've ever seen, right? With the exception of obviously very badly behaved non-differentiable function. But if a function is potentially differentiable, then you can do that derivative using the derivative rules. You have the product rule, you have the quotient rule, you have the chain rule. You have these really, really powerful techniques that let you take a huge variety of problems, and as long as you break them up into their independent steps, they're actually pretty easy. The issue with integration is that there aren't as many nice rules for that. We are going to discuss some nice rules. There are nicer ways of approaching this, but at the end of the day, sometimes you just end up at a dead end. And sometimes you end up at the dead end, and the only way to actually do your integral is to do what we just did here with the Riemann integration. Of course, if you're doing it this way, then you're probably using a computer simulation to do the Riemann integral, and you're probably pretty happy with rather than actually doing the limit as it goes to infinity. I mean, I don't know, maybe you're a masochist and you're actually doing Riemann integrals with the limits and you're using obscure summation notation and stuff like that. But you can also do numerical integration where you just do let a computer essentially compute, instead of infinitely many, you're computing trillions and trillions and trillions of areas instead. And then you use that as your integral or the estimate, and it's close enough that it won't matter for any purpose. But Riemann integration is legitimately sometimes the way that you actually have to tackle integrals. This is a technique that people actually use. So before I let you guys go, I want to give you guys just a handful of formulas that are really important for sums. That'll be important for actually evaluating the Riemann integral exercises that I'll give you. So let's see here. There's
so
yes.
I had a question.
Go ahead.
Basically, does it seems like the limit is impossible to evaluate if it has the summation inside of it, so you have to kind of find a way to get rid of the summation?
Pretty much.
And then
go on.
Well, I was just going to say, and then after you get rid of or cancel out the summation or whatever, then you can solve the limit. Is that basically what we're trying to do?
Pretty much, yeah. You got to get rid of the sum, because otherwise, basically, you have to take care of all the adding before you can figure out what the limit actually does, right? So if you want to actually find the value, you need to deal with the stuff inside. You need to understand what the stuff inside the limit says, and then you can evaluate the limit on the outside, right? The limit's on the outermost part, so it's the last thing you do when evaluating, right? When you're evaluating, you sort of always go from the inside out, right? You do stuff inside of parentheses first. So,
right.
Yeah, essentially you need to get rid of that sum, because we don't have a really good theory, like we don't have a really good thing for how does a limit and a sum interact. Can we push the sum limit inside the sum? The answer to that is absolutely not. The last problem is a good example of that, right? If we had pushed the limit inside of the sum, then we would have run into the same problem, right? The other issue is that because the bound of the sum depends on the bound of the limit, we can't pull the summation outside of the limit, right? The limit basically forces us to choose the bounds for our sums. So we need to evaluate that entire sum before we can evaluate the limit.
Okay.
Which is what makes this difficult, because there's not a ton of things that we're going to have nice summation formulas for. And I'm not going to expect you to do the really hard version of Riemann integration. That's when, if you're a grad student and you've locked yourself in your office for 2 months because you're trying to solve a horrifying integral that is basically impossible, then you can do all of this in its full awfulness. But the ones we're doing, you shouldn't have to lock yourself in your office for months. You
sound like you're speaking from experience.
No, I just knew. So I never had to do that because I wasn't dumb and I didn't go into applied math or physics or anything like that where you might have to do something so horrible. No, instead my problems were, I mean, I was still locking myself in my office, but like, at least they weren't integrals, I guess? I don't know. Don't go to grad school. It's bad. It's really hard. You can go to grad school if you want. I'm not going to... Never mind. Anyways, so there are 4 formulas that we're going to use for these types of exercises for evaluating Riemann sums. They are that the sum from n equals 1 to big N so first off, I guess there's going to be 5 of them. Of 1, is equal to big N. If you have, if you're just adding 1 to itself, big N times, you'll just end up with big N times 1, which is big N. It's not a very interesting one. The sum from n equals 1 to big N of little n. This is like saying 1 plus 2 plus 3 plus 4 plus da 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 da. And there's actually a really great story about this that has to do with the mathematician Gauss. And the story is that he invented this formula when he was basically in like elementary school. But the formula is that the sum of all the numbers from 1 to big N is going to be big N times big N plus 1 divided by 2. So the story behind this one is basically Gauss was goofing off in elementary school, and his teacher got really mad at him and said, okay, Gauss, go sit in the corner and add up all the numbers from 1 to 100. And like 10 minutes later, maybe less than that, Gauss was just like, nope, I got it. It's 50-50. And it turns out what he had done is he had written down the sum. And then written it down backwards underneath. And notice that all of these add up to the same number. And then it turns into just a multiplication problem. That's 100 copies of 101. But that was too big, so he divided it by 2. Right? So that's essentially where this formula comes from. There's also a formula for the sum of consecutive squares from 1 to big N. That's the one we just saw. That's big N times big N plus 1 times 2 times big N plus 1 divided by 6. There's also a formula for the sum of consecutive cubes, which is weirdly, and this is genuinely a coincidence, it's the sum of the single numbers squared. Big N's. And then a finite geometric series, which is the sum from n equals 1 to big N of r to the power of n is equal to, sorry, yes, that's correct, is equal to 1 minus r to the big N plus 1 divided by 1 minus little r. These formulas are found on page 238 of the textbook. So if you want to refer to them in a nicely typed up version, you can do that there. It'll also be in the printed out copy of the whiteboard notes if you didn't get them down here. So unfortunately, this is a section where it's been kind of nice for the application stuff because I've been able to primarily use stuff from Paul's online notes because I do like the way that he treats things like optimization and curve sketching and stuff. Unfortunately, I disagree with Paul on how to teach integration, and he does integration in an order that I don't really like. He does the punchline before the joke, which I think is wrong. We're going to be doing some more problems out of the textbook for this chapter. We'll still pull some problems from Paul's online notes instead, but specifically for this chapter, for this lecture, I should say, Paul doesn't have any of the ones I want to do, which is actually doing limits by hand. So I'm going to give you guys a handful of problems from the textbook, and then I'm going to throw together a little worksheet with some more problems that I'll post up in the channel in a little bit. Okay. Does anybody have any questions before I give you guys some problems?
For all of these summation formulas, they only work if n equals 1?
Yeah, there are versions of them for starting at a different spot. For instance, if you wanted to start at a different spot, like if you wanted to go from like j to big N, you could do the sum from n equals 1 to big N minus the sum from n equals 1 to j.
Right, okay.
Yeah. But generally, yes, these formulas are only for starting at 1. Okay. I don't hear any other shouts, so I will go ahead and stop the recording here. And I will send you guys